Hey guys, so I'm taking this really simple topic called collisions. And when I think of collisions, I usually think of really violent events when a car crashes into another car, or a plane crashes into a building, or demolition of new structures. But what I mean to say is, the collisions do not have to be necessarily very violent and intense events. So a collision is simply a meeting of two or more objects which carry a significant amount of momentum, right? And the simplest example could be clapping of hands, or giving a high five to your people, or sports. Every sport involves collisions. The bat with the ball with the ball, people with the people. But then in the end point is there are objects meeting with a significant amount of force and they exchange energies. So the purpose of this video is to analyze what happens to the object after they collide, right? And I'm taking a very exclusive approach of energy conservation where I divide this entire movie into four instances, and in the end, based on their energy, based on their total energies, I would conclude what kind of collision, what category of collisions they fall into. Right, let's just get started. So in my movie, the heroes are two objects, object A, object B. Initially traveling with speed v1 and speed v2. Assumably, speed v1 is taken higher than speed v2 because I would want at some point the objects to meet, right? And I'm making a very small modification. The modification is I'm taking a spring which is a massless spring attached to object B at the rear of object B, right? So the purpose of the spring I would explain at the end. Let's just keep it as suspense, right? Let's just get started, right? So this is that instant. Let us call this instant 1 at t equals to 0 maybe, right? So object A is traveling with object V1 and object B is traveling with speed V2. Let's just write the momentum and let's just write the total energies. So at this instant, the total momentum of the system is m1 v1 plus m2 v2. And the total energy at this instant will be only the kinetic energies possessed by the objects, which is half m1 v1 square plus half m2 v2 square. Now let's go to our instant 2 and let us make these objects meet, right? So my instant 2, let us say as t equals to t1, right? And this is that instant when the object A starts to meet object B, which means the spring starts to get compressed by some amount, say amount x, it's not matter much. So object A, object B, and then when the spring compressed by some amount x, you can very well realize by now that the spring will start to exert force. On object A, the spring force exerted is towards left, and on object B, the spring force is exerted towards right. Right, and we can really well conclude that the speed of object A starts to fall and the speed of object B starts to increase. But let's just not conclude those things. That does not hold a lot of significance to us. What holds significance to me right now is the total momentum of the system and the total energy of the system. Let's just stick to that. Right. Let us say at this instant the object A has speed v1 dash and the object B has speed v2 dash, and then the total momentum at this instant will be what? Yeah, sorry, m1 v1 dash plus m2 v2 dash, and the total energy at this instant I would write is half m1 v1 dash square plus half m2 v2 dash square. Cool. Let's move on to instant 3. Okay, no, instant 2 back. The spring has been compressed by some amount x, right? So let's just compress the spring and give the energy it deserves, half k. Alright, let's move on to instant 3. So instant 3 is t equals to maybe t2, right? Does not matter that much. So yeah, now it is that instant when the objects have come the closest they can, which means the spring has maximum compression right now. So when the spring has maximum compression, let us show maximum compression. Right, and let us say the maximum compression of the spring is x naught, and the objects are still going towards right. But then when I want to write the momentum of the system at this instant, again what will be the moment of the system? Let us say they have velocities v1 double dash and v2 double dash. So you would say that the total momentum is m1 v1 double dash and m2 v2 double dash, but that may or may not be true. My point being, when you look at this instant deeply, you will realize that both the objects are carrying the same velocity. How? So I just said that the spring has maximum compression, which means the spring is neither compressing at this instant nor decompressing at this instant, which means the ends of the springs are not moving. And in case they are not moving, the object A is not moving with relative to object B, which implies that they both are moving with the same speed. They do not have any relative speed. The relative speed is zero, which means both of the objects are moving with same speed. Let us say VA, right? So the total moment of the system will be what? M1V plus M2V, and the total energy will be half. Again, let's just take the common, half M1 plus M2V square plus, because the spring is compressed by some amount and which is the maximum compression, half K x naught square, right? Let's quickly go back to come to string 4, which is r t equals to t3, and this is where I make the objects depart, like the love story ends. And let us say after the spring has decompressed, the object B acquires say speed v2 double dash and v1 double dash, right? And again, I would you would want me to write down the total moment of the system, which will again be v4, which will be m1 v1 double dash plus m2 v2 double dash, and then the total energy will be half m1 v1 double dash plus square plus half m2 v2 double dash plus square. So I should be able to give you some conclusive answers, right, as to what sort of collision it is. Before I do that, I just write down these statements, see if they make sense to you. Total momentum initially is equal to total momentum at all instances, and total energy on the similar lines, total energy initially is equal to total energy in all the consecutive instants. Why? Obviously, because this is not a love triangle, so you see that there is no external force meddling into this movie, and also there is no non-conservative force involved. So both these statements hold true. Let's just focus on total energy initially and total energy finally. Total energy initially, if you see, is actually in the form of total kinetic energy, and total energy finally also, if you see, is also in the form of kinetic energy. So I can say kinetic energy initially is equals to kinetic energy finally. When this happens, I make my first conclusion, and the first conclusion is, when this happens, I say that this was the story of elastic collision. This entire story I told you was about elastic collision. And this is not what I promised, right? I promised that using these four instances, I'll be able to conclude all sorts of collisions. First, let me answer the question, why this elastic collisions? Look at instant 3. When you look at instant 3, the instant 3 has some amount of elastic potential energy stored. And instant 4 does not have any elastic potential energy stored, which means the objects have regained their shape completely and instantaneously. And this property, if you remember from your previous logic, we call this as elasticity. When this happens, when this particular thing happens, we call this collision as elastic collision, right? But then I took a very daring assumption in this entire derivation, going from instant 3 to instant 4, not showing any elastic potential energy left out in instant 4, right? So if this does not happen, when this elastic potential energy, some amount of elastic potential energy remains in the instant 4 as well, right? Let us say the spring gets, the final compression of the spring is x dash, so the spring potential energy becomes x dash half k x dash square. When this happens, which means it implies that the objects deformed completely and they tried to reform, they tried to regain their shape, but they were not able to, which means some amount of energy remained inside the object, right? Even though the total energy remains conserved, you cannot say that the kinetic energy remains conserved, because you can see very clearly that kinetic energy finally is actually less than kinetic energy initially. When this happens, we call this collision as inelastic collision. And in inelastic collision, you have a very special case of perfectly inelastic collision. What would perfectly inelastic collision mean? It would mean that the object has demonstrated perfectly inelastic behavior. Perfectly inelastic would mean that the object deformed and refused to reform completely, refused to regain its shape. When this happens, we call it as perfectly inelastic collision, as you can see in instant 3. When you stop your experiment at instant 3, when the objects just when this completely stops at instant 3, this becomes a perfectly inelastic collision. So again, in perfectly inelastic collision as well, your kinetic energy finally obviously be less than kinetic energy initially, because a lot of amount of initial kinetic energy, which was the total kinetic energy, total energy, has been lost in the form of elastic potential energy of the object. Now, why is it lost? It is lost because the objects compressed and then they refused to decompress, which means they took the energy which they refused to give back, right? When this happens, like the 100%, they refuse to give out the 100% elastic potential energy, we call it the perfectly inelastic collision. And perfectly elastic collision is very easy to see that. Look at instance 3, and you will realize that in perfectly inelastic collision, the final velocities of the objects is same. And this is how you talk about collisions. Thank you.